The DC motor. Basically some of the most important fundamentals and concepts of electromagnetism combined to make a small yet ingenious invention that powers almost all household appliances and is used in many more important machinery and industrial practices. And I'm here to show you how one is not only created, but how it actually works. When a current-carrying conductor is placed or interacts with a magnetic field, it experiences a force. This more simply is known as the motor effect. The force of a conductor can be given by, where N is turns of coil, L is length of conductor, I is current through the coil, B is the magnetic field strength, and sine theta being the angle at which the conductor cuts the magnetic field. A DC motor, as you probably already guessed, applies this motor effect to produce a torque by converting electrical energy into mechanical energy. To build a DC motor, two main components are required, the stator and the rotor. The stator contains a magnetic field and must stay stationary. So, multiple neodymium magnets were placed as such on opposite sides with opposite polarity to ensure magnetic field was generated. Next is the rotor, which consists of the armature and axle. For our armature, I just used the housing in which the coil was bored. I drilled 2 holes into it and used this wooden dowel as the axle. The coil was turned 60 times on each side, ensuring the directions of the current were the same. Now, the motor seems complete, right? Wrong. At this point, if I was to connect to the power, the motor would do a half spin and stop at the top and continue to wobble. This is due to the fact that the direction of current through the coil on one side will be opposite to that of the other side, causing an equal force both up and down, resulting in no net force, causing all motor to not rotate. Therefore, we use a split ring commutator and brushes to switch and alternate the current through the coil. By switching the current as the brushes maintain constant electrical contact with the commutator, the force will also switch every half turn, and the force graph will look like this. As you can see, I've made my commutator out of copper tape, and by sanding the copper wire, remove the enamel coating to ensure electrical contact with the copper tape. And see that small gap between the tape? That is the split to alternate the current. Put the copper coil through the copper tape and taped it all together to make sure the commutator stayed put. Now, I made the brushes like this by using 2 paper clips on either side of the commutator, and once electricity was turned on, the motor spun continuously. Force around a point or axle is also known as torque. The torque generated by a DC motor can be derived the following way. This allows the DC motor to rotate around the axle. The NBIA stays constant throughout the rotation, causing the only change in torque being caused by the change in theta. Theta, as shown, is the angle between the normal of the plane of coil and the magnetic field lines. Therefore, maximum torque is achieved when the plane of the coil is parallel to the field lines, as the degree between the normal and magnetic field line is 90, and sine 90 is the maximum value. Therefore, as the coil rotates clockwise, torque approaches 0 when in the vertical position, and this cycle is repeated throughout the coil's rotation, and the graph of torque over time can be given by the following function of sine. It looks like this. Now, you may be wondering, Kanav, will the coil continue to accelerate forever? No, as this will directly defy the law of conservation of energy, which states that energy cannot be created nor destroyed, only transferred from one object to another. Therefore, I will provide an explanation on how the DC motor doesn't defy this law by using Faraday's law and Lenz's law. Faraday's law directly states that a direct change in magnetic flux on an object will induce an electromotive force, also known as EMF, or voltage, causing an induced current. Now, suppose this induced current flowed in the same direction as the current the battery provides. This would also cause it to accelerate forever, once again defying the law of conservation of energy. Therefore, Lenz's law states an induced EMF due to Faraday's law must act in a way to oppose a change in magnetic flux that was a causation of the current in the first place. Therefore, the induced EMF in a motor is known as back EMF, as it opposes the supply EMF by the battery. The EMF in a coil can be given by EMF supplied take away from the back EMF. As the rotation of the coil speeds up, the rate of change of the back EMF also increases, displaying that the respective back EMF is proportional to the speed of the rotor. Therefore, back EMF maintains the same amount of total energy in a motor by reducing the mechanical energy produced by the motor by the same amount that the electrical energy increases. This is displayed through the following graph. As seen, when supply voltage equals back EMF, the motor is seen to spin at its maximum speed, also known as a design speed. This is due to the fact that once the rotor reaches this speed, total EMF in the motor is 0, causing no net force to be generated, in turn causing no further acceleration, ensuring conservation of energy. Another reason why back EMF is so vital in the function of a motor is it allows the motor to become self-regulating, meaning the motor always generates the correct amount of torque required for any magnitude of load, as shown by the flowchart. As the load increases or decreases, velocity of the armature changes in proportion, causing back EMF to also change and net current to be impacted, leading to another change in torque, and the velocity of armature will eventually return to the equilibrium, meaning the motor can continuously spin without having any constant maintenance. Thank you so much for listening to me on how a DC motor works and how it's created. I hope this helped you.